Okay. So I think homework 3 was due today. Was that good? How was it? Okay, cool. I will put out the 4th homework today later, but it's basically doing the same particle simulation that we did in 2, but in MPI. Yeah, so today's class is a continuation from last one. We will finish the send and receive discussion from last time, and then we'll do collectives, and then a little bit of theory for distributed algorithms. Okay, so last time we were talking about just basic MPI send and receive, and those are blocking versions, which means that the program doesn't continue until you finish either the send or the receive that you called. So for send, it does, or for receive, it doesn't finish until you have, there's a buffer on your end for the receive, and it doesn't finish until your buffer is empty or is full. And then similarly for send is not finished until the send buffer is empty. So it has been transferred over the network. And the completion time depends on how big your message is and how much buffering was there in the entire system and also in the network. You can also call non-blocking send and receive. So non-blocking means that it returns immediately and it returns some handle that you can tell, you can query the handle to say whether it's done or not. And you can do test and wait, which are functions that respectively test whether the function is finished or wait until the function is finished. So yeah, so the function headers, they're called iSend and iReceive, which are the non-blocking send and receive. And these include 2 new MPI types, which are request and status. And then you can also wait. So send and receive will give you status and request, and you can wait, and you can use those as handles for these calls to tell whether they're done or not. And you have to, so you pass in, just like in regular send and receive, iSend and iReceive also take data buffers, but you cannot access the data buffer until you wait, and then the wait tells you that it's finished, or test, and then test tells you that it's finished. If you try to access the data before you've tested it, that's undefined because you don't know if the send or receive has finished. Okay, so this is the exact function header for iSend. Just like regular send, it has buffer, count, data type, recipient, tag, and communicator. And these are all the same as regular send. And the last one that you have to pass in, which is different, is request. And it's just a handle that you can use later to check on the status of this call. So this is non-blocking send. And again, you have to check the buffer before you use it. And to check the buffer, you can use wait, which waits for this non-blocking operation. So you basically, I'll show you some code for it later, but the way it works is like you call iSend, then you do some stuff, and then you call wait. And then you can't continue past wait until that operation is finished. And the parameters for wait are request and status, where request is the handle to the thing that you passed iSend or iReceive into. And similar for test, it checks if the non-blocking operation is finished. And the difference between test and wait is that wait, like you can't proceed past this time, past this point, and test, it'll just give you true or false.
So does wait like converted to a blocking operation?
Yes, but you can put the blocking later. So like if you just call send or receive, the blocking happens at the send and receive.
Yeah.
Yeah, but exactly, yeah. So wait is a blocking wait.
So like if you've done everything you can do while waiting.
Yeah, exactly. Yep.
Mm-hmm.
Yes, so I will show you an example of what it looks like. So suppose that we are the sender and there's some omitted like enum up here, but you want to send this number 12345, and you call iSend with this number, and these are just the regular parameters to send, and then you pass in request, which is just this empty handle here. And then you do, if you can do other stuff, you can do it here while you wait for the send to finish. And then you call, as you said, like now you call wait, you finished all the stuff that you can complete up here, and then you can finish the function. Yep. So like I said, in this case, sender is 0. So process 0 will send the value, and then you only continue after the send is finished. And on the receiver side, so this is just case receiver now, and case sender is just what we just had. Receiver, you can call regular receive. You don't have to call iReceive if you called iSend, and vice versa. And then once you receive it, your process 1 will receive the same value, 12345.
This is similar to asynchronous programming?
Yes, yeah, so you can, in that the send and receive are asynchronous from the rest of the computation.
And as we, when you require non-blocking send, it may create a new thread to take care of this.
Yes, it can create a new thread underneath.
Can you remind me how MPI receive knows who it's receiving from?
Yeah, for sure. So received is just this buffer, and this is the number, this is the type, and this is the source. This is the source, this is the tag, and here you passed in 0, or this example passed in 0 as the source. Okay. So we just use iReceive, but this is the function header for iReceive, which is pretty much the same as receive. But again, now it has the request at the end, which is just the handle to tell you if you use, yeah, this is the non-blocking version, and this is the handle that you can test and wait on later. Okay, so that's all I want to say about send and receive. Just to recap from last time, we talked a lot about network topology, and there's a lot of them, and each of them has their own strength and weakness. The main performance metrics for our network are latency and bandwidth. And MPI, we did some MPI last time, and the core functionality that we talked about last time, and also a little bit this time, is send and receive and variants of send and receive. Yeah, so I guess I can stop for questions if there are any. Okay, good. So now the main functionality for MPI that I want to talk about today is called collectives. So collectives means that every process is going to communicate with every other process in the communicator. And remember that the default communicator is just all the processes that you had, but you can like with specialized functions set subcommunicators. So for example, broadcast, which is you have some value here, a sub 0, and you send it to everyone else. Scatter, which is you have an array and you send one element to everyone else. And gather, which is like the inverse of scatter. So everybody else has one element and then you send them all to one processor. The most basic one is broadcast, and broadcast takes in a buffer, which is this array that you're going to broadcast, an int of how many things you want to broadcast, data type, the emitter rank, which is the source rank for the processor that's going to broadcast, and then the communicator. So everybody will call broadcast, whether you are this one or these, like whether you're the source of the destination, and only the source will need to actually send the thing. And you can kind of think of broadcast in all the collectives as not like I am broadcasting or I'm receiving broadcast, but like I'm participating in broadcast. And the rank just tells you who is the source.
Where are you putting the data?
The data is in buffer.
Okay, so like, but the one person or one process has to put something there.
Yes, everybody needs a buffer either to receive or to
Sure.
send. Yeah, but only one needs to have something in here. Like emitter rank needs to have something in here to send it. Yeah. Okay. And scatter. So you have send data and you have send count. Send data is an array. Send count is the number of things that the source will send. These are similar, like data type, receive data type. Receive count is how many things each process will receive. And data type. And then again, we have a root, which is the source that's going to scatter all the elements. And scatter takes this array and it distributes them in order of the process rank. So process 0 would get the first piece. Here it's red. Process 1 would get the green one. 2 gets this blue one, and then 3 gets this teal one, and so on. And these don't need to be one element each, like they can be arbitrarily sized.
Where do we define how exactly those separated or like?
So this for scatter, they all are even sized, but they can be larger than 1. There's a version called scatter v that also takes in an array of how many values you're going to send to each one. So an array of length, how many processors you have, and then you would put how many elements you send per process.
Is it like similar to broadcast where everybody just like kind of call the broadcast function in a way and like participated, but like is it the same here?
Yes. Yes, so everybody will call scatter. Everybody, even the receivers will call scatter, but receivers don't need to pass in anything useful for send data. Only the source needs to pass in something useful for send data, and the receivers need to pass in something useful for receive data, because this is the buffer that they will get the data into.
Okay, I didn't get the part how exactly the data is partitioned into the like, how do we know whether like the red block is going to rank 0 and then the green one to the rank 1?
So like as the source, you pass in some array here equal to length number of processors. you
Oh,
want.
okay, but it's
Yeah.
just like equally. Over.
Yes, yeah, so it'll just equally, like, if you pass in one, then it will just equally divide it up into chunks of size one and
Mhm.
scatter them to the destinations.
Okay, and that would go to send data as an argument or where?
Send data is the data send data is this thing, and receive data is these things.
Yeah.
Does that make sense?
So in the MPI broadcast, all the receivers have to call broadcast possibly to conversion.
Yes, for collectives, everybody needs to call either scatter or broadcast or whatever it is.
But in broadcast, I didn't see a receive button.
For broadcast, everybody just uses buffer because send and receive are the same. Or send and receive are the same size. But in scatter, like send will be cut up into pieces. Sorry? Yeah.
What's different about receiver?
Receiver needs to pass in buffer, but it doesn't need to pass in any useful value inside buffer. It can just pass in empty space. Like after a broadcast is finished, the receiver will see whatever send had in buffer in their own buffer.
How do you know who the receiver?
Emitter ring. Yeah. Okay, so that is scatter. And gather is just the inverse of scatter. So instead, now you have multiple processes and they're all going to pass in, they're also all going to send their value to some source destination or to some destination. The function header is very similar, but now root is the one that you send them all to. And yeah, so it's just the inverse of scatter, and you often use it for like sorting and parallel algorithms in distributed memory. And like I said, gather and scatter also have different variants. Like there's so many variants of gather and scatter, but one of them is gather v and scatter v, which you can give it a length, an array, and the array has how many elements from everybody or to everybody that you want to send to for gather and scatter. So this is kind of a picture, like this is, everybody has a different length of array that they're going to send, and then they all get gathered into this one. Okay, so let's look at an example of how you would use this. So the function that we want to do is we have some list of numbers, and the list of numbers is spread across all of the processors, and you want to average all the numbers. So first, if your rank is 0, then you would first create all the random numbers, which is however many elements you want to send per processor times the total number of processors that you have. So here the root is creating the array, like the array that we're going to compute on. And then to store those numbers, every process needs to make a buffer to store that subarray of random numbers that they will take, which has length elements per process. And then you're going to call scatter. So everybody calls scatter. There's no like if your rank is something, call scatter. Like every processor in your world is going to call scatter. And the source is random numbers, which is the random numbers that we generated, elements per process, which is how many elements we will send to every process. The type is float. This is the destination array, which is subarray of random numbers. This is the length, elements per process. The type is still float, and then the source is 0. And after this is finished, everybody will now have this elements per process number of random elements in their buffer. So then you would compute the average on this array, just you sum them up and you divide. And then you would gather. So yeah, you compute the average on your own process. So this part can happen in parallel. Then the root needs to make a buffer to create all these, to hold all the averages that all the ranks computed. So then you call gather to now gather all these subset averages that everyone computed. So subset average is an array for the root, and everybody is going to send you the root 1 element. And the type is float. The I guess this is, yeah, sorry, it's source and dest. So this is the source. It's just 1 element for every rank. this is the destination, which is an array, and then the type is still float, and the root is 0. So the root is going to gather all the averages that everyone computed. And then it's going to compute the final average just by computing average on the averages. And this is what an example of what it would look like when you print at the end, like average computed is this one single float. Does that make sense? Yes.
That makes sense. But like, I'm wondering, what would happen if we didn't have the very last if branches? Because like, in my logic, we populated the array anyway, right? So what would happen exactly? So would then just every node, so to say, try to compute the average, and then only the node with the rank 0 would get the actual average over all subsets? Of what would happen in terms of computation each
see.
node individually?
Okay, so if we go back a little bit, only rank 0 here allocated enough space.
Okay.
And then because, yeah, so then you could do the gather, but the other ones would crash because they didn't have an array
Yeah.
to compute this average. But if they did make an average, like if they did allocate it, but they just didn't gather onto it, they would, all the other ones would compute garbage.
Okay, but only then the rank 0 would have the actual.
Yes.
In the previous one, the sub-randoms will be shared across all the processes, or is it specific to a particular process?
There's one per process. Every process runs this entire function.
How does MPI, like, what sort of factors it considers while optimizing data movement as compared to me just calling like send or receive?
What do you mean? What kind of
So
factors?
I can just like divide the data myself and call in as calls to send data
Mhm.
over the network. And
Yeah.
get it back.
Yeah.
As compared to this, what does MPI optimizes by considering data movement?
Like for like gather and for collectives, you probably want to do some kind of tree like send and receive. Because if you can implement gather, or you can implement scatter just by like sending, as you say, to every process to every rank in the world. If you send them serially, you're going to serialize this entire process because the sends happen in serial.
No, I can just like fill up multiple threads for send. If I-
Yes, but there's like some limited number of ports, or like you have limited network bandwidth per machine, or like limited sending capability per machine.
That's limited for MPI.
That's limited. That's like a hardware limitation.
Yeah, but yeah, that's limited for MPI.
Yeah, it has nothing to do with MPI. Like MPI is just the software.
This time it's limited, I'm just, my question is like, on the software side, what would MPI do different than me just calling like send manually?
It would do like a tree so it would send to like, if you imagine a binary tree, it would send to like 2 parts of the binary tree, and then those 2 neighbors would send to their neighbors. Because now you can utilize more send ports. Yeah. Does that answer the question? Mhm. Yeah. So yeah, that's how you would use gather and scatter to do average. Okay, and then there's also functionality that you can do all gather, which is similar to gather, but just in gather, all of these blocks would go on one route. For example, if you call 0, all gather does it on all of them. So it's very similar to gather, and the function header is the same, except now there's no root. Yeah, this is called many to many. The other ones were called many to one or one to many. And we could use all gather, like this is kind of related to your question. If you used all gather in this average example rather than gather, then everybody could compute the average. There's no like if rank equals 1 or rank equals 0. Now everybody can compute the average because we called all gather and everybody has an array. And so everybody could print the same average.
Why would we do this instead of just gathering it in one rank and then computing and then broadcasting them?
Good question. So I deleted the example from the main lecture, but for example, if you wanted to compute standard deviation, where everybody needs the average of everything, like average is easy because you just wanted to compute one average. But in standard deviation, everybody needs to compute like a subfunction, like everybody, the expression for standard deviation needs the average of every single thing.
Okay, but still can't we just gather them and?
You can gather them to one and then you could broadcast together.
Yeah, yeah, that's
Yeah.
what I'm saying.
Oh yeah, you could do
What's
that.
the difference between that?
Well, I mean, obviously, you can do something, you can compute like different things, like, you can do like 3 different values based on the same, right?
Yeah, I mean, yeah. I think-
Yeah, for this example, like you wouldn't really need to use altogether. This is just like an illustration to show how you would use the function header, but for different algorithms or for different things, like if you needed, you may need everybody to have the total average or some total aggregation.
But I suppose under the hood altogether has anyway, like the same logic, like just like.
Yeah, you can implement,
gather broadcast,
yeah, you can implement it with gather and broadcast.
so it's like a short.
Yeah, pretty much.
And how slow would this be compared to gather and also compared to what we're talking about by gathering and then broadcasting back? Is that the gathering and broadcasting back would reduce the total number of communications versus in this case, you basically have to do it with all the processors, they have to communicate to each of them
Mhm.
in like a fully connected network, right?
Yeah, sorry. So the question was, how fast would this like all gather be compared to just gather and broadcast?
Yeah.
Probably similar, because I guess maybe it would be a little bit faster because in gather and broadcast, you'd have to wait for the first one to finish before you do the broadcast. But in this one, you don't have to. You just everybody uses all their incoming ports.
And what about also like clogging up the network? Like, we're talking about, like, when the nodes are communicating with each other, sometimes they can be inhibited because of that, because it's not much.
I see.
But so many different processes all communicating with each other
Mhm.
in like the maximum possible manner.
Yeah,
Would that be?
I see. It's really hard to prove anything about queuing. So like usually in the easiest models for analyzing distributed algorithms, you only count communication. Like queuing is not really a cost in most of the simple models, but it would definitely be a factor if you were sending a lot of data. Yeah. So in terms of collectives, there's also, like we were talking about, you can do reduce. So reduce just does everybody has some value and then you call some function. Here is sum, but you can call max, min, so on. And then those all get reduced onto one process and you have to specify the root process. And then again, you can do all reduce, which is the same as reduce, but like it's like all gather, but instead is reduce. So everybody has some, in this example, a vector, and you just do this reduction over the first element, and that's the first element in the output, and reduction over the second one, and that's the second element in the output. And then it's the same as, like I said, it doesn't need a root, it's just reduced, but without a root. Okay. So we'll go through an example about how you would use these functions. Suppose that we want to compute parallel rank. So parallel rank is everybody has some, this is your starting state. Everybody has some number. So 0 would have 5, 1 has 2, 2 has 7, 3 has 4. And you want to, in parallel, compute the ordering of the numbers. So like this one is the smallest, 2 is the smallest. So 1 would get rank 0. And 4 is the second smallest. So 3 would get rank 1 and so on and so on. And you can easily see how you would do this in shared memory, like you could sort the numbers. And we are basically going to sort the numbers, but you want to do it in parallel. Or you want to do the entire thing using MPI because like suppose that the numbers all started in different ranks. Yeah, and the application that you might want to use this in is suppose you're doing some benchmarking. So every MPI rank runs some process or runs some function, and then you get some runtime for that function, but they're all running the same thing. So they have you can tell like which process is faster than which other ones. So this is the function that we're going to implement. It takes in send data, which is one number, which is the overall thing that we're computing rank on. It takes receive data, which is going to contain the rank data at the end, takes data type, and it has the communicator. So the input is one number per processor, which is the numbers that we're going to compute rank over, and the output is the rank one number, which is the rank per process. So the first step is we're going to assume that you can gather all the numbers into the root. So first we will just gather them. You know the size of them. It's going to be equal to the number of processes that you have. So you first allocate an array on the root that can hold all the numbers and just call gather. Okay. And then now we're going to sort. Sort is easy. We have sort in like C++, but the challenge is that you can't just sort directly on the numbers because then we lose the original information about where they came from. So we need to make this struct that has the number, either it's float or int, and the rank that it came from. So yeah, that's the owner, and that's the number that we're going to call sort on. And then, yeah, so like I said, we're gonna so we're gonna get the ranks. We make this data type, and then we create an array of these structs equal to com_rank number. Or sorry, yeah, we created an array of these structs equal to, with count equal to the number of numbers that we gathered. And as pre-processing, we're going to attach the correct rank just by doing like a sort, or just by doing like an iteration. And we took in gather numbers as an input, and those are just going to go in order. Yeah, so you just copy in the number that we got from the input, and then you call sort on the second number, and the ranks are still maintained because we just had the ranks originally. Or yeah, so now the ranks are just the order that they appeared after the sort. So ranks is just defined like this. Yeah, so the ith element in the sorted thing is the ranked value. You can clean it up, and then afterwards you scatter them. You make an array for the ranks to just like copy the rank information, and then you scatter the ranks. Yeah. This is the workflow of what it would look like. These are the numbers that we started with. We gathered the numbers, we attached the owners, we sorted by the actual numbers, we extract out the rank information, and then we scatter them back out. Does that make sense? Yeah, and that's basically what this, what the output would look like. This is your number on your process, and you print out the rank. All right, that is all about MPI. Are there questions? Okay, so for the next part, I want to talk about how you do theoretical analysis for distributed algorithms. So recall that we had this PRAM model in shared memory, and in PRAM, all memory access operations were in one clock period. In regular PRAM, there's no memory hierarchy. Like the memory hierarchy is a separate model that you can combine with PRAM, like with factors of M and B, but in regular PRAM, you just don't have any concept of the memory hierarchy. And it is good to understand whether or not you have enough parallelism. So we talked about work in span before. And in PRAM, you assume that you have infinitely many processors, and the span again is the length, like if you had infinitely many processors. And a reasonable design strategy for doing shared memory algorithms is first you design something that's good in PRAM, and then you worry about the memory and communication. And sometimes this works and sometimes it doesn't, because often for memory, you might have to reorder, or like you might have to rework your representation, and that might affect your parallelism. But this is one thing that you can do, and maybe did happen in homework too. Okay. But PRAM doesn't exactly translate that easily to distributed memory models, because you have these machines, and then each of them has may have many processes, and then they have to do this communication, which is more expensive than it is in shared memory. In shared memory, we had to do memory movement from DRAM, but DRAM is much faster than moving something across the network. Okay. So the first most introductory model for distributed memory machines is called latency and bandwidth model. And the way it works is that you can count, it basically only counts communication, and it counts the time to send a message parameterized by the length of the message, I guess in bytes, or I guess here it's in words, but it can be in bytes. And then time is equal to latency, which is fixed regardless of how much data you send, plus n, which is the length of your message, times the cost per word. And that's equal to n, the length divided by the bandwidth. And this is called alpha beta model, and alpha is the latency and beta is 1 over bandwidth. And then usually alpha is so latency is much bigger than bandwidth usually, and both of those are much bigger than the computation time. So in latency and bandwidth model, you're not counting communication, or you're not counting computation. Yeah. And so this model captures some things, which is good. So it captures the fact that if you have one long message, that's faster than sending many short messages, even if you send the same number of bytes, because you're saving this latency startup cost. And you can do a lot of flops for the cost of one message. And we're not even counting flops. Similar to in the external memory or in the cache line model, we didn't count computation, we just counted cache line transfer. So this tells us that you need a large computation to communication ratio for your algorithms to be efficient. So slightly more complicated, and this is one of the most popular ways to do the analysis, which is called bulk synchronous parallel. And the way it works is that you have this high-level abstraction of a machine, and it has these different components. First one is that you can do local memory processing, kind of like how we were doing in MPI. Everybody does their own local processing, and it has a network which can route messages between pairs of these different processes, or all of the different processes, and some kind of hardware that allows you to do synchronization across all of the hardware, or along all the processes. So to do analysis in BSP, it works like this. You capture your algorithm into large super steps, and super steps are like this. The first part is you do some computation. So every processor can do some local computation, which you can overlap with communication in your actual software. And then you have to do some communication in which you exchange the data between all the processes. And then after that, you do a synchronization. When a process reaches the barrier, it waits until all other processors have reached the same barrier, and then you can start again at the next super step. Yeah, so like I said, you can overlap the communication with the computation, and it's hard to say when any single communication will be finished because it depends on, like you said, it depends on how many communications there are in the network and the congestion and so on. But this BSP model provides this upper bound to how long it will take you to communicate a set of data. So suppose that you have H incoming or outgoing messages in some super step, and they're just saying this upper bound is some parameter G, which is how much time it takes to send one message it takes to send a message of size 1, and then it takes time H times G to send the message. So this ignores the latency, this is different from the model that we just had because this doesn't distinguish between if you send one big message or many small messages. But this is just how they had it in the original model. And yeah, and then the last step is the barrier synchronization. So in this model, there's some cost L to barrier synchronization, and it's just plus L in every super step. And then the cost of barriers depends on the variation in the completion time, which is if some process was way longer than all the other ones, then you would have to wait for that one to finish. And also there's some hardware cost to reaching consistent state, you have to do basically like cache coherence, but in a distributed system. So putting all these factors together, there are 3 costs in every super step. The first one is the cost of the longest running computation. The next one is the cost of the global communication among the processors. And then the last one is just the cost of synchronization. So that is synchronization cost is fixed across all the super steps. So this is just the expression. So you take the max over all the processors of W sub I, which is the cost for the computation. You take the max of H sub I, which is how many messages you're sending or receiving in process I, times G, which is the cost of sending one word, plus L. So you always have to do L. And then if you just sum these up over all the super steps that you have, then that is the cost of your algorithm. Okay. And one of the main applications for this is BSP is underneath platforms like Pregel and MapReduce, which are these popular platforms for graph processing. So they kind of work like this. They have MapReduce especially, it has the just super basic primitives. It lets you do map, which is you apply some function over all your data, and then reduce, which is reduce like we were doing before. And it turns out that you can express a lot of algorithms using just map and reduce. But you can think that like map would be one superset. And then reduce, like you have to do some communication, and then you have to do some, yeah, so like you could do map in one superstep, and then you can reduce in another one. Okay. So yeah, that is BSP. Does that make sense? All right. We always go back to matrix multiplication. So we have n by n matrices, and we want to compute C equals A times B. And now suppose that we cannot fit the entire matrix on any one processors. So this is the most simplest way that we could do matrix multiply. So we partition A and B into P square blocks. So we have A, B, C, and each of them gets partitioned into P blocks. So the length is n divided by root P along each dimension. And so you can order your processes in a grid. You have P sub I and J, P sub ij, and initially you store the same corresponding tile, Aij and Bij, and that can help you to compute submatrix Cij. But that's not the end, because we know that we need this entire tile row and this entire tile column for A and B. So like I said, you need Aik and Bkj for everything in this range. So what can we do? We can do all to all for all the blocks of A in every row and all the blocks of B in every column, or in every tile row and in every tile column, which is the same as like the processor row and processor column. Then each process has all the tiles that it needs to perform computation of its submatrix. Does that make sense? All right, so how much did it cost? So we're going to use BSP. In step 1, we did root P rows of all tall broadcasts. Each has size n squared over P. So that would be G, which is just the cost of one word. This is the cost of each submatrix, and this is the cost of how many submatrices we had to send. In step 2, we do the same, but for the columns instead. And then that's just the same thing as in the rows. So the total communication time is this plus this, which is 2G times this is many matrices we had to send. So that is the communication time. In terms of the computation time, we have root P multiplications, and each of them takes this much work each, because this is the side length of your matrix, and the cost of cubic matrix multiply is this to the power 3. So the total computation time is we had to do root P of these multiplications times the cost to do one multiplication, which is n cubed over P.
Is that possible to overlap communication and computation using ISIN and IC?
Yes, it is possible, but here the computation depends on getting the result of the communication. Like you need the submatrix to compute this submatrix multiply.
Right.
But you could do like one, you don't have to wait for all of them to arrive before you do one of them. Yes, that is true. But that is hard. Like you definitely have to do at least this much communication time, because like assuming that you have to serialize the communication. You could overlap some of this computation time, but it's hard to say like exactly. Like you cannot just take the max of the computation and the communication. Yeah. So this is like a worst case analysis where you just sum them up, but you could do better. And actually in some models, you just ignore the computation time, so you just count the communication time. So to finish it up, the total time in BSP is the communication time plus the computation time plus the synchronization cost. Okay. So there's this issue with this algorithm, which is that every process needs to hold the entire block row and block column for AIK, BKJ. So every process P sub I has two root P blocks of each matrix. And so everybody needs theta n squared over root P, which is an extra root P factor on the total size of the matrix. Because we had, like originally we just had size theta n squared, but now everybody has copies. And so there's this extra root P factor. And we would prefer not to use that much extra space. Okay. So there's this old famous algorithm for doing distributed matrix multiply. Yes, it's super old now. Now it's from like 69. It's called Cannon's algorithm. And basically, it's going to try to maintain the same bounds as that simple algorithm that we had, but to improve the memory efficiency. And the idea is that we're going to add more rounds and then compute the addition of only one. You're going to do one tile addition per round. And the way it works is that it's based on this formula. So Cij, normally it's like, it's like Aik times Bkj. But here, they note that it's in the subscript here, it's I plus j plus k mod root p. And that is independent for all ij. It's not obvious that it's true. I think that's like why it's interesting. So, so previously, like when we had the simple algorithm, everybody, you can think of just summing over k in this intermediate like dimension. But now we're going to sum like different k for every block row and column. And so that is going to use different submatrices. So this is a depiction of how it works. So this is your initial set of A and B. This is just 3 by 3. So you start with A00 and you go to A22. And same with B, you go to B0, you start at B00 and then you go to B22. And you have to do some initial rotation. So starting from A, you kind of rotate this first row 1 to the left. And then you rotate the second row 2 to the left. So here we had A11 was in the center, now A11 is in the left. And then previously A22 was in the lower right, but now A22 is in the lower left. And we had a similar story for B, except instead of row-wise, it's column-wise. So we rotate B11 up, you rotate this one up 1, and then you rotate this one 2 up. And then and you would do this like for arbitrary n. So you have to do this initial alignment. And notice that now the k dimensions are matching, like A02 and B22 will help you compute C02. And then same for the other ones. I guess 00 is obvious, but A01 and B11 computes C01 because you're just matching the outer dimensions. Or you match the inner dimension and then the submatrix you're computing is the outer dimensions. So you do this initial alignment and then you compute like some partials of your submatrices, and now you need to just rotate again. But so A rotates left and B rotates up. So now we had A00 here, and now we're going to pass the first row 1 to the left. So that gets A01, and everybody gets passed 1 to the left for A, and everybody gets passed up 1 for B, and then you do some rotation.
Maybe I just didn't understand her. What are the considerations with a matmul here versus like how are there different considerations between here and like before, which is like a SMP?
You can't fit the entire matrix on
Like
one processor. Yes. And like maybe you can, previously we had it was still like less than n squared, like in that simple algorithm, it was still less than n squared, but it was like the total usage was over n squared, asymptotically more than n squared. Yeah, so the considerations are like if you cannot fit the entire matrix into one machine, you have to cut it up. And the most natural ways to do it into like, you cut your, you arrange your processes into a 2D grid, and then your 2D grid corresponds to your matrix. Yeah, so So suppose that you can only hold like one tile of A, B, and C at a time. And so you need to, in the next step, you would just pass everybody to the left for A and pass everybody up one for B. And you would again do the tile multiplications, but here, notice that the intermediate dimension has changed. So this was C00, but now it's A01 and B10, but before it was A00 and B00. And so on, like in the next step, now the intermediate dimension changes again. But the intermediate dimension is not the same for everyone. So here, like in the upper left, the intermediate dimension was 1, but in just one to the right, the intermediate dimension is 2. And then in this one, the intermediate dimension is 0, and that's how like the rotation works. Everybody's intermediate dimension is different, but the outer dimensions are still right. And the way that you do that is through the rotation. Okay. So this is just the pseudocode, but it's a bit hard to read, so you can just kind of imagine the picture, which is probably easier to understand. The main step is that in every step, you have to shift one left in your block row, and you have to shift B one up in your block column. And then you multiply your submatrices to accumulate them into C sub ij, and then you do this however many processes you have in your row. So we're going to do the analysis in BSP. The initial step, everybody has to do a circular shift in row and column directions, and the submatrices have size n squared over p. And so the communication is just 2 times n squared over p times g, where g is your cost of moving data. And in subsequent steps, everybody has to do the circular shift of the same communication cost, and they're root p of those steps, because you have root p row and column dimensions for your processors. And so that is just multiply this thing up here by root p. So now this denominator became root p rather than p before. And you add them up to get your total communication. To do the computation, there are square root p plus 1 super steps counting the initial alignment step. So then you just multiply the number of super steps by the cost of synchronization, and the computation time is the same as the original algorithm, n cubed over p. Make sense?
So the previous algorithm, the issue that you mentioned was the fact that like it didn't like if you had like original memory, because it didn't use all the memory space, but like over time it used a large amount of memory on like one processor. Was that the issue?
Yeah, it was that overall you used more memory, like the whole volume of memory was bigger, and also the memory per process was bigger. Like here you only have to hold 3 tiles per process at any time. There you had to hold 2 times square root p. Yeah, because you have to hold the entire row and the entire column. And you just vary k to do the entire submatrix multiply. So here you're trading rows, or you're trading rounds for memory. Because there you do the entire thing in one round. I have backup slides. So I made this shorter because I wanted to get through the analysis, but I have more examples. So I guess we can do questions first, and then I can go back to MPI. Okay. Oh, sorry, yes.
Is this like, I think the best we can do? Because I mean, this is kind of old.
Yeah, is this the best we can do? No. There are more modern algorithms. The most popular one is called Summa. And Summa, the way it works is that, this is for inner product, which means that you vary the internal dimension, like the shared dimension. There's outer product matrix multiplies, which you basically do like partials for the entire thing, and then you add them up. Yeah. And so Summa is based on outer product.
Why is that faster?
Why is that faster? I think it's I think it's less rounds. Yeah. But you don't have to know the actually even have to do the analysis for the homework. I think the main takeaway is that you want to minimize the communication. And also ideally minimize the number of rounds. Yeah, okay. Oh yeah, I do want to talk about broadcast actually, because you had a question. Okay, so to answer the question better from last time. Going back to broadcast. This is, yeah, so this is how you call broadcast. And this is like a naive way that you would implement broadcast. So like you said, if you're the root, then you just do serial 4 and then you call send to everyone. And then everybody else would call receive, and that would be totally fine. That would work. Better would be this serializes your broadcast. So better would be to do this tree-like thing. So if 0 is your root, then in the first step you send to 1. In the next step, 0 sends to 2 and 1 sends to 3. Because now you can double like your output in some sense. And then in the next, and so on down the tree, like you double the amount of processors that could send the data at each level of the tree. So you would need to take, rather than n rounds for the serial version, you would take log n rounds. And this is some experimental data about how the scaling works. So this is the serial version. This is actually calling MPI broadcast. You can see that it scales better with the number of processors. You're utilizing more bandwidth, yes. But doing the serial one is not saturating bandwidth. Like memory bandwidth is on the order of like gigabits per second. You cannot saturate network bandwidth with one sender.
What about saturating, but like generally data centers would want to use less bandwidth because it's very expensive.
Mhm.
Yes. Compared. You want to pass messages, you would want a very minimal number of bandwidth as compared to performance because passing messages is very convenient.
Yes, like in that if you can trade communication, if you can trade computation for communication, you would prefer to like that.
No, you are trading like performance for communication. And if you were to just do a linear saying from node 0
Mhm.
to every node, you would have n minus 1 message
Yes,
as compared to this very hard X number of messages which is greater than n.
here you would still have n messages. The number of messages is the number of nodes in the tree. Yeah, but is your point that like you would sometimes? Oh, okay. Okay, so that is broadcast. I already did scatter, so I don't need to do this. Yeah, I guess we could do this. Okay, so I said that you can call MPI reduce. For reduce, it's pretty much the same as all the other collectives. So this example, again, is doing averaging over the entire thing. Each processor still does the random numbers. Then you do the local sum again per process. And now you call MPI reduce, and there's one single local sum that everybody is aggregating into onto the root, and the root is 0 here. And then at the end, if you print the global, yeah, you want to print the global average on root on rank 0.
Yeah, so like MPI sum, that's like some operator, like, can you put like, or like, is there like a set of things that you put there, or can you put something like custom, or would you have to like write something up to?
Yeah, you can put, there are some preset things like there's sum, there's multiply, I think there's max and min, but you can put, I think you can write your own function and pass it in.
If you wrote your own function, would you have to like handle like, I don't know, like this something like with the reduction, like do something tree-like thing, or I don't know how this is implemented, but like.
Yeah,
Would
it's
you
probably
like
also
have
like a
to
tree.
like do the, what, good implementation for it to be good, or would like?
Oh, no, you can pass in, like, here's MPI sum, you can probably pass in any arbitrary function here, but the reduce, like, the communication pattern stays the same.
Okay.
You're just passing in a different function. And the function just
Or,
needs to,
I meant like, we talked about like a few lectures ago, like with the, like, the scans, or
Mhm.
what you mentioned, what are they called?
like the prefix sums?
Yeah, something like there are different ways to do that. Is it like,
Oh, like the different prefix sum algorithms, you
Yeah.
mean like up sweep and down sweep and stuff like that?
Yeah.
Yeah, I think here they probably implemented the same as with broadcast, like in a tree. For reduce, like the tree is probably the best. There is also MPI scan, and for MPI scan, they may introduce those fancier algorithms. Yeah, so this is what your output would look like. You aggregate the entire average of everything. Yeah, okay. So this is what I was talking about earlier, which is that suppose that we wanted to compute standard deviation. And this is your expression for standard deviation. You have some list x of 1 to x of n. And this is your expression. You sum over like the sum of squares, or sum of squares minus the mean. And everybody needs, everybody can compute this part separately, but everybody needs n and everybody needs this to compute it in parallel. So this is how you do it with all reduce. First, you have everybody compute your look. So the first goal is to compute like the denominator. No, the first step is to compute the average. So you're just going to compute the average like we did before. You're going to compute this local sum, and then you do all reduce to get the mean on every single process. And I think you just get the denominator for free, like the number of processors times number of elements per processor. And the mean is your global sum, which you computed through all reduce, divided by this thing which you had for free upfront.
Wouldn't they all have a different mean?
No, this is one mean over the entire list.
Okay,
Yeah.
then what is each thread, or what is each process calculate?
Each process is calculating
Oh, this.
like a
different
sub
points
list of this
for
thing.
them.
Yeah, like this is one giant summation.
And then they like reduce that all into one.
Yeah, you're gonna reduce all, the only hard part is calculating this thing in parallel. So you're gonna like calculate chunks of it, and then you're gonna aggregate them all, and then one thing can just do the square root at the end. So yeah, so you partition the list, you compute the total global sum, and then you compute, like I said, you compute this sub list of squares, sum of squares. That's just your number minus the mean squared. And then you call reduce of all of those onto one processor, because you're just trying to compute the numerator. And then you can just one rank needs to compute this square root. And then that's it. Oops. Does that answer your question?
Yep.
Yeah. We did MPI reduce. You can also do scan. The interface looks exactly the same as reduce, but you do inclusive scan and you still pass in the function. Yeah, you can also split the communicator. So up until now, we only had one communicator, which was CommWorld, which was everybody. For some cases, you might want to have a subset of the communicators. Like you might want to, for example, if this is your entire world, you might find it easier to express your algorithm if you partition it into rows. And so the way you would do that is called CommSplit. And CommSplit just creates a new communicator. You create a group of subcommunicators from your initial communicator. So this is the function signature. This is your initial communicator, like in the initial state, this is the entire world. And you pass in a color and you pass in a key. And the way to read this is everybody with the same color is going to be in the same new subcommunicator, and key is the ordering within the new communicator. And the old communicator is still there. This is just going to return a new one into newcom. So this is an example of how you would use it. You have, so your total rank originally, this is your initial rank in the total world. This is your initial size of the entire world. And in this example, you have 16. And so the color is going to be your rank times 4, which is the row that you're in. And so MPI CommSplit, every processor is calling split, and then every processor in the same row is going to get the same color because we just did division by 4. And then you still pass in the same world rank. It doesn't need to be indexed by 0, because the world ranks in the new communicator are going to be just ordered, like no matter what. They don't have to be indexed off 0. They're just going to be ordered from whatever they got passed in.
The new communicator MPI world, or is that, would it be different?
You can name it whatever you want. Here it's called rowcom. So you declare a new communicator yourself and then you would pass it in. Yep. So yeah, you just give it like a handle. Yep. So like I said, you get the rank and size of the communicator from the beginning. You define the color and then you pass in the ranks. Here in this example, you just pass in the same ranks that you had originally, and they are ordered in the ranks that you pass.
So how does the ROCOM begin?
The rowcom, each of these is like a separate rowcom. So in the original, everybody has this is world. Everybody has world in the beginning. And now after you pass in rowcom, what was originally 0 through 3 has this rowcom. What was originally 4 through 7 has this rowcom. And so on. Yeah, and then this is just some print, and then this would print the size of the new world, the size of the new column that you had. Yeah, the size of the old one and the size of the new one. And then this is what it would print like. This is your initial rank, this is the initial size, and this is your new rank, and this is your new size. So it will automatically start the ranks from 0. And this has been reordered to look better. Like in normal processing, they would print in any order. Okay. That is all I had. Questions?